Sorry. No. Okay, so I'm going to bring the meeting to order again if I can in the room and online.
Right.
And we have another two talks and a brief discussion before we break for lunch. It's my great pleasure to introduce Buzzard, who is going to talk about the state of the art in the formalisation of research level mathematics. Thank you, Gary.
Thank you very much, Barry. And also thank you to Cam for the invitation. I spend my life carrying around lean stickers. So anyone who's in the room, if you want a lean sticker, let me know. 3 lean stickers. So I was asked to talk about, well, I can't remember if I was asked or if I suggested, but I'm going to just talk about the state of the art, the idea that you could use this software, that we just saw Patrick using it to prove, things like, to prove basic first-year undergraduate analysis. We've seen it doing that, and so now here's a different question: can we use it to prove the kind of theorems that the mathematicians expected the math department to publish? So in contrast to using systems like this for teaching or developing undergraduate level material, there's a far briefer history. So I'll just go through that in 25 minutes. So just one slide on how it started as far as I was concerned. And then Athena knows full well how I ended up using Lean. I chose it randomly in some sense. And I started doing it, and I started engaging with the software because I wanted to use it for teaching. That's where I came from historically. So the idea was take some complicated system that knows the axioms of an equivalence relation and stick it in front of a bunch of struggling students who can't put together a coherent proof and show them that there are hypotheses and assumptions and the goal and everything is all just a big game. It's like playing chess. And that's what a proof looks like. There's concrete rules and you do it like that. So that was not what happened at all in practice. I put this complicated software in front of all these students, and the vast majority of them didn't understand what was going on at all. These people were struggling to understand equivalence relations, and now things are twice as bad because they've got to understand A, equivalence relations, and B, this really complicated piece of software. But the really, really smart students that already knew what an equivalence relation was already, they started coming to my club instead and wanted projects. And so I gave them some master's level commutative algebra to do, this first year undergraduates, because I knew that sort of stuff was kind of easy to do in this software, and we ended up defining schemes. So it was a disaster in terms of trying to teach undergraduates how to use this software, but it was a weird success in the sense that there's 4 undergraduates who've got some publication. And I go around telling people that teaching Lean, a scheme was something invented by Grothendieck in the 1960s. It's the building block of modern algebraic geometry. So we type the definition into Lean, and I go around telling people how easy it was, but actually when you reflect back, we got stuck a couple of times teaching a computer this sort of what I would call basic modern algebraic geometry. And so one reason we were stuck was that the literature was, quote, wrong. What's the smallest ring containing the integers and a third? Well, if you think about it, it's got to be a ring, so you can do addition and multiplication. And so you're allowed to do a third times a third, which is a ninth. And you're also allowed to multiply by any integer numerator. So these 2 rings here, well, the first one is definitely the rational numbers A over B such that the denominator B is a power of a third. But then if you think about what's the smallest ring containing the integers and a ninth as well, well, if you're allowed a ninth, then you're allowed 3 ninths, and 3 ninths is a third, right? If you've got a ring containing a third, then you can make a ninth. And if you've got a ring containing a ninth, you can make a third. So those rings look pretty equal to me. And they're equal if you regard them as subrings of the rationals. But if you regard them as abstract localizations of the integers at some multiplicative set, then they're not equal anymore. They're both equivalence classes, but the equivalence classes are just completely different. So Grothendieck identified localizations when they gave morally the right answer, when they gave canonically isomorphic answers, and Lee was like, no, they're not equal. So that was one thing I ran into, and another thing I ran into was dependent type L, where you push forward an open set along the identity map, and you get a slightly different open set, which is obviously the same open set. Right? It's the same because they've got the same elements, but somehow it might be different in another sense. And I was desperately trying to use the identity function between things which a mathematician would say were the same, but Lee was like, well, actually, they're kind of slightly. There's a whole fuss about what it means for two things to be the same. Like Lee just has a different opinion to my mental model. So there were some struggles, and this is just doing stuff that was sort of standard stuff from the 1960s. So the big question is, does it scale? And at the time, the answer was, we don't know. One big problem was that the area, this was back in 2018, and the area was popular. Most of the people working in the area were either computer scientists or there were these random undergraduates that I got interested. I mean, most people were computer scientists, so they weren't really interested in research level mathematics. Because, you know, it's not the kind of thing they study. It's not really, and then some of them are mathematics undergraduates. And so, of course, the obvious thing to do was not try and do research level mathematics in 2018, not least because we didn't actually have a basic undergraduate degree, which is clearly a necessary prerequisite. A basic undergraduate degree where all the theorems in a standard undergraduate curriculum were all there in the same place. That was a very natural project to do, especially because the people I was working with at the time were undergraduates. But there were many, many other people also realizing that this idea was quite sensible. And we had some kind of viable structure for making it happen. We had Lean, which was being supported at the time by Microsoft. And we had this fledgling mathematics library, which was being maintained by some very smart young people who had really decided to spend a lot of their time dealing what my undergraduates was throwing at them. So, of course, the problem is that making some undergraduate level mathematics won't get you a paper. And so if you're a computer science PhD student, you have no desire just to like build the basic theory of matrices, because it's probably been done somewhere in another system. Well, who's going to publish that? But it's a necessary prerequisite to get you anywhere. And my undergraduates were not looking for papers, they were just looking for things to do over the summer. And other people as well, they're somehow, you know, we didn't care about the nature of the mathematics, we just cared about making the object. So this sort of happened organically around 2018, 2019, this basic mathematics library that people like Patrick are using without mention. You know, the stuff that has this idea of like the limit of a sequence and continuous functions and the definition of a topological space. This all happened around that time, 2018, 2019. Of course, historically, there had been one big success at that point in terms of formalising modern. Yeah, there have been lots and lots of theorems proved. I'm talking about modern mathematics. And the quotes, the most modern thing we had was not done in Lean at all, it was done in another proof assistant, and it was Hale's. So he proved this 350-year-old conjecture of Kepler that the best way to put spheres in three space is the obvious way. This has been open, phenomenally hard problem, had been open for centuries. And Hale's proof was computer assisted. He reduced it to a lot of hard work. He reduced it to a finite check, checking 70,000 non-linear inequalities, and he checked them all using some C code or C++. So he had this proof, and the annals sat on it for 5 years, and eventually they accepted it. But there was a little warning in the publication that the referees hadn't actually checked the computer-assisted part. Right? The referees were not able to check that these 70,000 non-linear inequalities had actually been proved rigorously. Like if there was one bug in the code, then the proof was wrong, and they didn't understand the code. And so Hales was infuriated by this situation and decided that he was going to prove it himself. So he formalized the proof using these higher order logic systems, and it took him 12 years. And then we had this was a mathematical proof for which Hales had won prizes, and we now have it formalized, right? So there's proof that computers can formalize modern research mathematics, although it does take 12 years. And also, it's not a normal proof, right? This is a computer-assisted proof. And this is not the first time we've seen formalizations of computer-assisted proof. The four-color theorem was another famous example. An infinite problem, brilliant idea, reduces it to a finite but very tedious problem. Check that 2,000 graphs, satisfy some properties, and then a computer finishes the job, and then a proof assistant can also finish the job as well. And that was what we had, and somehow the area wasn't taking off, and that was where we were. And so Patrick, the previous speaker, and I had this idea at the same time and independently that we should actually go for something which the mathematical community would recognize as somehow fashionable modern mathematics. So we knew that Scholze was going to win a Fields Medal. This was 2017, 2018. We knew that Scholze was going to win a Fields Medal for his work in perfectoid spaces. So we just thought we'd do perfectoid spaces. And as I say, the idea is we need to target the kind of mathematics which is winning Fields Medals, as opposed to just proving that the sum of the limit is the limit of the sums. So there's a very different idea to teaching. And as I say, we had problems with schemes, and it wasn't really clear that perfectoid spaces, we're not talking about proving profound theorems about perfectoid spaces. We just knew that all of a sudden people would be saying, Peter Scholze won a Fields Medal for defining perfectoid spaces and using them to prove lots of brilliant theorems. And we just thought we'll start with just defining perfectoid spaces. That was the plan. So we're not going to prove any of the hard theorems, and we had no idea whether it was feasible. Of course, this represents fashionable modern mathematics in a very, very weak sense, because the actual thing that had won Scholze the Fields Medal was proving the theorems, and we were just going to do the definition, right? So this is a publicity stunt. We were both completely, there was no secret. It's the first thing we say on the first page of the paper. So Johan Kommerland was also involved. He appeared very shortly afterwards, and the three of us formalized the definition. And we wanted to do it before he won the Fields Medal, but it took a while, so we ended up doing it in 2019. And it wasn't plain sailing. We did get stuck sometimes. We had to ask computer scientists for help, but it worked. And even though teaching Lean what a perfectoid space was and teaching Lean what a scheme was, are formally just the same thing, right? You just type in a definition. But when I was going around telling people we'd formalized schemes, nobody was interested at all. And when I was going around telling people that we'd formalized perfectoid spaces, people got really excited. So the publicity stuff worked really well. I had no idea the systems were so much, but it is not that difficult to read the definition of a perfectoid space and then type it into Lean. But it worked. It absolutely worked. So now, here are some more examples. So in some sense, before the perfectoid space work, we had, we had the cap set conjecture. So this was a theorem proved in the Annals of Maths. They resolved an old conjecture, and it took about 2 years to formalize the entire thing. So that was like an Annals of Mathematics paper from 2017 was completely taught to Lean by 2019. And that Annals of Mathematics paper was 4 pages long. That was one of the first crucial things. It was really short. But another crucial thing was that actually it didn't use much mathematics, apart from undergraduate level mathematics. There was sort of one thing it used that wasn't undergraduate level. But a phenomenon that we observed was that they needed our maths, like this undergraduate maths library, to formalize that work. And then conversely, some of the useful lemmas they needed went into the maths library. So doing research mathematics made the maths library better, even though the maths library at that time was concentrating on undergraduate. So that was exciting. And then Patrick launched the next big project, which was this theorem that you could turn a sphere inside out. So this is a theorem with a long proof. The proof is old. It was proved in, I think, the 50s. But there was a new proof that was discovered in the mid 2010s. And Patrick's idea was that actually that proof could be formalized as well. And this was a milestone, this project, because not only was it really the first time where we really had a non-trivial proof in Lean. This is a long proof. This proves that Lean can handle non-trivial proofs, but also Patrick realized that we needed this infrastructure we have where we turn mathematical proofs into really cool looking graphs. I mean, I could just probably switch over. I was going to show you this later, but there's no reason not to show this now, right? See if I can find it. Oh, that was just, there we go. There's another project, and it's let's see if I can zoom out. There we go. There, there's a giant piece of mathematics there, and you can sort of zoom. Like blue means it's not been done yet. Blue means it's been stated, and green means it's been proved. So this software was developed as part of this project. And again, this was new mathematics because the theorem was old, but the proof which was formalized was new. And it was sent to a journal, and one of the referees' reports was kind of like completely farcical. It was like written by a computer scientist who complained that there was no definition of the two-sphere. The theorem is about the two-sphere. So this is an indication that it's being sent to. So the system is broken because where do you send papers like this? At the time, there was nowhere to send. You send it to a computer science conference proceedings, and then it gets reviewed by people that don't know the definition of the two-sphere. So that was a bit weird. But then in 2020, the real breakthrough happened, where Peter Scholze came along and said, "Okay, you can formalize one of my definitions, but can you prove one of my theorems?" He'd isolated a lemma in his work which nobody had read. And he asked me if we'd had a study group at Imperial on this work, and I said yes. Then he said, "Did you read the proof of this lemma?" And I said no. And he said, "Yeah, exactly. Like no one is reading the proof of this lemma." And he conjectured that the referees wouldn't read. What's really going on is he conjectures that in 5 years' time, he might be able to use his theory, to prove the global Langlands conjectures or the Hodge conjecture or something. And then everyone would be very excited. But it all builds on this lemma. And then maybe like some random PhD student at Harvard is going to send him an email someday saying, "Oh, I tried to read the proof of this lemma and I got stuck here. It turns out the lemma's wrong and everything's wrong." I think that was what he was worried about. He just wanted someone else that wasn't him, Clausen, to actually read this lemma. So he couldn't find any human that would read it, and so he challenged us to, read it to the computer. That was the idea. And the lemma was not, it's his modern research mathematics that's very important in some sense, but it's also a very, very basic. There was not much advanced stuff going on. He chose very well the challenge. This is just there's a lot of it's not particularly difficult arguments about groups with filtrations and maps between groups with filtrations. So he proved this lemma, and he got super excited and wrote a blog post about it, announcing that firstly we'd fixed all the errors in there were typos, and there was like the first thing I did was he had some argument and the proof was by induction, and I started off and the inductive step was fine, but the base case was wrong. And that is really not uncommon. I've also seen a TIA get a base case wrong. So two Fields medalists at least have failed to do the base case. The base case is important. So firstly, we fixed all the errors. Secondly, we greatly simplified the argument because there was a bit that looked really complicated. So we were putting off formalizing it for ages. And then eventually we realized we didn't have to. We realized exactly what we needed to get from the theory, and then we realized that actually that meant that we didn't need the theory. We just needed the corollaries of the theory, and the corollaries we could just about prove by hand. And he also claimed the whole process taught him what made the proof work. And so that was it then. That was somehow the turning point. Next thing we know, suddenly nature is interested. So this project, as I say, this was a challenge by Scholzer to prove something. It was very clever because what he really wanted to, what he personally wanted to know was whether there was a mistake in his 10-page messy undergraduate level lemma, right? And this lemma, our maths library was very well suited for checking this lemma. You know, that's why we could do it. That's why we could do it in 6 months. But what he actually challenged us to do was not prove the lemma, because that would be kind of technical and boring. He challenged us to prove a corollary of the lemma, and the corollary had a 5-line proof in the paper. But the corollary was a statement in homological algebra, which was an easy consequence of the lemma. But that made us develop a theory of homological algebra, which wasn't in the maths library at the time, because that's fancy maths, right? That's not undergraduate maths. This is sort of fancy maths. And we developed that theory. It took us a year. It took us 6 months to type in 10 pages. And then it took us a year to type in 5 lines. It's sort of, you can't guess. Because we had to make a theory first. And once we had a theory of homological algebra, we found out that actually we couldn't really use it. And that was also, like version 1 of schemes we couldn't use, and version 1 of other things we couldn't use. But that's okay, because you try it and then you get a definition, and then you realize the definition's unusable, and then you understand the mistakes you've made, you realize what you should have done, and then you just do it again. So, you know, schemes version 3 was the version that ended up in MathLib, and similarly, homological algebra version 2 was what ended up in MathLib, which was developed by Joel Hieu, Patrick's colleague in Orsay. In Saclay, sorry. So work of Babic Messer. So now I'm just going to go through a list. The last 8 slides are just a list. We've got Erdős's unit fractions conjecture. This was proved in December 2021. So this was a new proof. 6 months later, the entire thing was in use. And similarly, bounds on Ramsey numbers. So some breakthroughs about 18 months ago. And again, Babic just sat down. He wanted to read the paper. So we thought, why don't I read the paper by translating all into Lee? And he did that in summer 2023. And in both cases, the theorem was announced. Babic formalized the proof. So Messer formalized the proof. And the proof was completely formalized before the referees, the reporters on the paper. So there you go. Modern combinatorics you can actually do in real time if you're an expert. And it's the right kind of modern combinatorics. We'll see another example of that in a minute. And one reason this is happening is because you want to formalize a random theorem of Scholzer, then suddenly you need all the theory of homological algebra. But if you want to do combinatorics, you need things like polynomials and vector spaces. And all of that's in the maths library now. You know, very robust, a very robust, well-tested development, which can actually be used in practice. So that's why combinatorics is accessible, and analytic number theory also. Whereas the kind of algebraic number theory that I do, it relies on thousands of prerequisites, thousands of pages that isn't there. So another trick, me and Jeremy Abigad, who's also speaking, I think, today, we organised a conference at IPAT. Me and Jeremy and several other people, but one of those other people was Terry Tao, who was interested in, how machines could do mathematics. How can machines help us to do mathematics? So he got interested in that. So of course we stuffed a bunch of lean talks into this conference. So he saw it, and it took him a year to come back to it. But a year later, he decided he was going to learn it, and he'd formalized an elementary result and blogged about it. He proved an elementary thing. He found some cool new argument. And there was some Math Overflow post where he explains the argument, and he thought, why don't I formalize it? And it turns out that he divided by zeros. So that was, lean tells fields medalists they've divided by zero. I mean, it wasn't a serious division by zero. Like, you just have to change some, you sort of slightly change the statement, and you change the bounds a bit, and it's fine. But he did actually divide in version 1 on the archive. You can see a fields medalist divided by zero. So that was exciting. And then in November, he proved a big conjecture with Tim Gowers, Ben Green, and Freddie Manners. And 4 days later, he announced that actually, why don't we try this as as well? So this is the polynomial Freiman-Rüscher conjecture announced on the 9th of November. 13th of November, he announced he was going to formalize it. And again, so this is not because he thinks the proof's wrong, right? Because he thinks it would be interesting to see what happens. So he spent most of his time making the blueprint, taking the 38-page paper and adding further explanations and getting other people to do it. So he's adding details which aren't in the normal paper, but the idea is you add in lots of extra details and then undergraduates can come along and formalise and help you. And the entire process just took 3 weeks, which is quite extraordinary, really. So it was a massive success. So again, it's sort of combinatorics-like stuff. So all the prerequisites were there, but you can do 38 pages in 3 weeks if the prerequisites are there. So it was all managed on the Lean Zulip chat, and it worked great. So 2 last projects. One of them is the Carlson project, announced by Floris van Doorn in June. So Carlson's theorem is the theorem about Fourier analysis. So it turns out to be incredible. It looks very similar to a theorem you saw as an undergraduate, but because you say converges pointwise almost everywhere, that makes it incredibly difficult. I can't really comment on why, but what's happened very recently, Christoph Thiele has proved a stronger theorem, and the proof is not yet published, but actually we do have a 150-page PDF in the blueprint, and the idea is that this entire thing is going to be formalized. So we don't know how long that will take, because now less of the prerequisites are there, because it's not combinatorics, it's analytic number theory, and we're going to have to make, analytic number theory, for harmonic analysis, there's loads of standard theorems in harmonic analysis, which are quite tricky, and some of them are there and some of them aren't there. So the lean code is just beginning to appear, but the idea is you can just join in, right? You can go to the website, you can see, it's all being managed on the Lean Zulip as well. You can go to the website, you can see what's happening, and ask to join in. So the progress currently seems to be great. And then the last thing I wanted to mention, well, there we go. If Tao can do 38 pages in 3 weeks, then obviously we could do this whole thing in 4 months. And the answer is no, it's going to take years, because the prerequisites are missing. So finally, I'm running a project to formalise Fermat's last theorem. Starts in October. I mean, you could look at the work now, but there's nothing really there. But what I'll actually prove is that all the prerequisites to the Taylor-Wiles papers imply Fermat's last theorem. So that's the first goal. And I think that 5 years should be fine for that. So again, I haven't really started seriously, but hopefully August. And so again, the idea is, well, it's only 200 pages, so we should be able to do it in 1 year, right? But of course, again, the problem is there's no prerequisites. And another thing worth stressing, I think, is that I'm not formalizing Fermat's last theorem because I think the proof might be wrong. I'm formalizing because I know it's not wrong. And that's another thing that I think the computer scientists find it sort of surprising that they can't get their head around this. But there's another proof around now. And I'm not going to formalize that. But on the other hand, if Mochizuki wants to try and formalize it, then I'll certainly be open to helping. But maybe that's a good time to stop. All right. Thank you very much.
Thank you very much, Kevin. And really helpful rundown into the history of how it's been used in your research. I think we need to stop sharing the screen.
Oh, that's a good idea.
Yeah,
Oh, Patrick has raised his hand, but you're not going to allow him, are you?
No, we're going to try and wait till a bit till after Heather's talk to take questions and discussions, but do drop them in the Q&A so that you don't forget it. So, Heather, are you able to share your screen? Wonderful. And if you just unmute, we'll just check that we can hear you.
Can you hear me?
Yes, we can. Fantastic. So as I say, we will take questions and discussion after Heather's talk. A pleasure to introduce Heather Macbeth, who's going to talk to us about a calculation-heavy introduction to proof with support from them. Thank you, Heather.
Thank you. And thank you for inviting me to this workshop with some familiar faces and some new faces. I'm very happy to be here and to have a chance to talk about some of the experiments that I've done teaching with Lean at my institution, Fordham. So I wanted to start by telling you about the course in which I've introduced Lean. So this is my department's course for first and second year students, which serves as their introduction to somehow rigorous mathematics as opposed to sort of the computational mathematics of high school. We call it discrete mathematics, but really it's a kind of introduction to proof. It's got some logic, what they call proof techniques, a little bit of elementary number theory, and then sets, relations, and functions. And I put this departmental syllabus up to show you that I really committed from the start of introducing Lean to this course to try to keep teaching what was traditionally on the menu for this course. I didn't want to push the envelope too far, and I wanted to make sure that it still ticked all the boxes that were required by my department. So part of the reason is that I didn't have total freedom in this course. This is a course which is taught at my university in so-called sections of about 20 students. And at the same time that I teach my version of it with Lean, there are other sections being taught to other groups of 20 students by other people. This is the standard model at my university. And so, the students coming out of my section needed to be able to slot into the same future courses as the students coming out of the other sections. So these are first or second year American students. They've typically taken 2 calculus courses, sometimes 1, and they're just dipping a toe into this more rigorous proof-based world. So I started teaching this course in 2023. I've now taught it 3 times with Lean, having previously taught it 6 times without Lean. And since last semester, 2 of my Fordham colleagues have taught it with Lean as well, using my materials and some innovations of their own. And in addition, 2 other instructors at somehow similar contexts, John Bannon at Siena College and Sina Hazratpour at Johns Hopkins, have used the materials again for somewhat similar courses. These are all private institutions with relatively small class sizes and a certain degree of flexibility at this level to teach it in this way. So I want to briefly sum up the pedagogical goals I have for a course like this as being to teach mathematics in a way which is rigorous but concrete. I think that sometimes introduction to proof is used as a course in which students become accustomed not only to proof-based mathematics and to mathematical rigor, but also to the idea of abstraction. And I think that although these two things are confused, they're actually a little bit different. And somehow the abstractions, can even be more of a jump for students than the rigor. Looking at, abstracting several different things and seeing that they're equivalence relations, for example, I think is more of a jump for many students than simply requiring a higher degree of precision in the logical reasoning that the students are doing. And I think in any case, these 2 things can be separated. So I think Lean can help with both abstraction and also with precise logic, but I think it's easier to use it for the goal of improving students' logical reasoning. And for this reason, I try to defer all of the abstraction in the course to the last month. For the first 2 months, I teach very familiar mathematical objects, but with very careful logic. And the more abstract novelties come only at the end of the course. So let me start by giving you a sense of the materials that I've developed for this course. So I've written lecture notes totaling about 300 pages, which you can find online in draft form, and which are also under consideration for eventual publication. So I hope you'll see that soon. And the style of these lecture notes is to combine several different ways of presenting the same material. So I'll introduce a problem, And then there are somehow two languages in which I solve such a problem. I'll write it in the kind of concise, mature mathematical style that students are trying to learn in this course. And I'll try to also give a lean proof, like you'll see at the end of this page. And then in between these or around these, I also give the informal commentary that I hope it helps explain to the students somehow what these two mean. And I emphasize this because I think that for students at this level, the concise kind of grown-up mathematician style of writing is already a foreign language. Sometimes you see this problem addressed in textbooks at this level by trying to write the proofs in a more informal style that explains to the students how you might come up with proofs. But I think, personally, I find it more instructive to give the style that you're hoping the students will achieve as a direct sample, and also to give this informal commentary to explain to the students how they might find their way to the concise style we're aiming for. And given that this concise, grown-up mathematical style of writing is already foreign, it ends up not being too much of a mental leap to the students to teach them two foreign languages at a time rather than one foreign language, the second foreign language being this writing in lean. Here's a quick glimpse of the table of contents for the course, and as you can see, it really does cover pretty closely the standard syllabus for the course at my institution. And there are perhaps a few novelties just in the organization of the material, the order in which it's treated, as opposed to the content itself, which I'll get onto later. I think the big novelty is probably just in how you design the beginning of the course. So as I said, these materials have now been used by some 5 different people in teaching courses of a roughly similar structure. And so there's been a certain degree of variety in how all these people use them. But for myself, here's what I would typically do. At my institution, these courses are taught in 75-minute classes. And I divide such a class roughly into thirds, with the first and the last of the 2/3 being devoted to a completely traditional Blackboard lecture, and the middle third being devoted to lean. And of that lean time, most of it is interactive work by the students. I find that after the first couple of weeks, each new day's material can be taught in lean quite quickly after the students have seen the Blackboard version of it. So having done a detailed Blackboard lecture on material, it usually only takes about 5 minutes to explain to the students how the corresponding lean commands work. There's usually only a couple. And so most of that middle third is spent by the students working on the lean problems in class. I would say the most important component of making this really work is that there's some flexibility in how the credit for the course is assigned. There's a real risk in a course like this that if you don't somehow require the students to learn lean, they won't do it. Perhaps this is not an issue at institutions with really excellent students, but I think at most institutions, students only do what they get credit for. And so I think the most important thing that makes this work for me is that I am allowed to put a certain proportion of the credit to the course on the lean itself. And so I have homework worth 25% of the final grade, relatively small number of problems, but not all that easy. And half the problems are exactly the same on lean and on paper, and half of the credit for the homework comes from the lean. So the students, do have this enforced learning of lean sort of asynchronously in order to get their homework done each week. And then in addition to that, because I think for any kind of coding course, there are plagiarism concerns, I furthermore have tests assessing the lean fluency of the students. And again, I think this is important. Students, a certain proportion of them, are always going to copy and paste each other's answers. And I think the easiest way to guard against this is to be able to speak to them live so that they realize that they do have to learn the language themselves. So I devote quite a bit of time each semester to 2 interviews per student of about 20 minutes each, in which they solve brand new lean problems live in front of me. And, you know, these are graded rather leniently, but they provide the necessary spur to make the students actually learn lean, which I think is important if they're going to get the benefit that one hopes for from it. And then the rest of the course, the final exams are completely traditional, you know, very similar to the way that I would give the exams before I taught the course in this way. So in Patrick's talk, there was you know, Patrick gave a detailed treatment of quite a few of the themes that I think are really important in teaching with lean. And I think the one that I really want to call attention to is the question of skill transfer. We all hope that when students, you know, encounter lean in the context of their first encounter with proof, that the interactivity that they have with lean that lets them go back and forth and work towards quick feedback and learning how to produce correct lean code transfers to the ability to write proofs on paper. And as Patrick noted, this really is not something that you can, this is not something that comes for free. It's something that you have to carefully design your course in order to ensure. So I think there are several things that go into the question of how to design your, how to design the lean code that appears in your course in a way that that encourages this skill transfer. So one, of course, is writing lean in controlled natural language, the way that Patrick did. This is not something I've experimented with yet, but it certainly is, I think, one component of this broader goal of keeping the lean and the text as close to each other as possible. Another component of this that I know that some people have experimented with is the question of how you describe the individual steps of the lean code. So there are usually several different sort of idioms in a language like lean. You can, in particular, there's a famous dichotomy between procedural and declarative proof styles, where procedural tends to mean that you explain in each step what is being done to move forward sort of one step, you know, what transformation is being needed to go to the next step. The declarative proof style is more like you say the next thing that you would like to deduce, and then you leave it somehow to the automation to figure out what should be done, what logical transformation, what computation in order to get there. On paper, because there isn't the sort of auxiliary of the proof state, the info view, we are enforced to largely write in a declarative way with a few procedural elements. And so I think there are certainly many people who feel strongly that the declarative proof style is more convenient in terms of encouraging skill transfer. And I agree with this to a certain extent, although I guess the issue with the declarative proof style is that it tends to be more verbose, which can impede student experimentation and is also a little bit tricky when dealing with novices who make frequent syntax errors. Somehow, the more they have to write, the more risk there is that they'll make mistakes. So I have developed a kind of hybrid style for my course, which I hope combines the two of these in some relatively pragmatic way. But this is still not somehow the place where I've really focused my work. For me, the place where I've really focused the most is on keeping somehow the implicit sequence of the proof, the implicit story of the proof, as close as possible to the paper proof. This has some connection with the forward reasoning versus backward reasoning dichotomy that Patrick discussed in his talk. I think there are certain ways of writing proofs that are uncommon on paper and are easy to do in a proof assistant, but which it's better to avoid in a proof assistant because they tend to be tricky to translate to paper. And so I found myself avoiding such things and instead developing a sort of dialect of lean, which aims to contain only commands that are relatively easy to translate to paper, but at the same time are flexible enough for the needs of the mathematics I cover. So here's a typical example from my course that shows some of the new automation that was developed for my course. So this is what I mean by a proof in which I've really tried to, which I think really exemplifies the goal I've had of keeping the sort of steps of the lean proof as close as possible to what you'd write on paper. So this is a recurrence relation, y0 is given, and then yn plus 1 is given in terms of yn. And you have to prove a congruence fact for all natural numbers n by induction. And on display here, you can see a few of the tactics which I developed for the course in order to make the reasoning closely follow, as you can see, the reasoning on paper. So on the left is a prose proof, and on the right is what the students would write in lean. So notably, the rel tactic, which is used in the last two steps, is a tactic written by myself and Mario Carnero, which applies somehow substitution rules for relations that are not equality, for example, congruence or inequalities. The point being that on paper, if you want to deduce from A congruent to B, mod 10, that 4A plus 1 is congruent to 4B plus 1, you don't say, by the reflexivity, multiplicative, and additive rules of congruences modulo n, you simply write it down and allow the reader to infer the structure. Another custom tactic is this extra tactic, which identifies somehow neutral elements modulo n. In this case, the 2 times n is neutral modulo 10 in some sense, and therefore you can remove it when you have an addition modulo 10. So part of the work of designing a language like this is looking for steps such as this, which really are done as a single step in the minds of mathematicians at this level, and writing up automation that precisely covers this and nothing else. Here's a second example illustrating this same rel tactic, but in the context of inequalities, where the usage is a bit more subtle because side conditions of positivity also need to be checked. And here's a third one, again illustrating that I try to keep the two fairly similar, and illustrating a few other tactics I've had. And I mean, the takeaway, without necessarily following the lean line by line, is just that you can see there's a heavy reliance on these declarative calculational proofs in such a way that the key component that you're training the students to construct, namely these left to right chained calculations, is something they can directly transfer to their homework on paper. So just a couple of notes to the experts, a very sort of heavy emphasis here is that there's an emphasis on having a language of tactics that is nearly sufficient for the whole course. So there's a sort of trade-off in writing mathematics in a system like lean between tactic use and lemma use, where lemmas are literal theorems from the library that are being invoked. I tend to find lemmas very unfriendly to students for a couple of reasons. Firstly, somehow if you sort of firstly, they tend to not somehow record how people think about things on paper. Usually, like in the case of this modular arithmetic example that I mentioned, the sort of orchestration of the lemmas to prove a style of thing is done more somehow algorithmically, more algorithmically, sort of as a one-shot observation by the reader than in a kind of precise and literal sense. So if on paper we don't tend to write the precise rules we're using, but just run the algorithm in our heads, then the students shouldn't have to call those lemmas by name. But there are also real discoverability and searchability problems for lemmas that make it quite tricky to design a course which is heavy on lemmas in this way. So a real priority of mine in designing this kind of lean language for my course was to minimize the number of individual things that needed to be memorized by the students. So in the end, the tactic library is a bit bigger perhaps than is necessary if you stick to many lemmas, but the number of lemmas used in the course is, I think, certainly fewer than 50 and possibly fewer than 30, depending on how you count. And so if you restrict to a very small number of lemmas in this way, I find that this sort of demand on the student memory is less, which ends up being rather convenient. So a related point here is that the sort of idiom of lean that I developed for my course is not really designed to help the students discover proofs, which is kind of interesting. You know, you can imagine an approach that, you know, and I think Patrick's widgets, for example, have some relationship to this, which really aims to help the students discover the proofs. And by contrast, the idiom that I've developed really only functions as an enforcer. But by restricting to this tactic language, I somehow am able to enforce what I consider to be good style. And I think that part of teaching students at this relatively early level is enforcing stylistic patterns that don't come easily to students, but do serve them in good stead later on. So, for example, this heavy emphasis on the calculational proofs, like left to right chains of reasoning, you know, for various relations, that really has to be taught to students. I think many of them don't pick it up naturally. And you can enforce this kind of reasoning by not providing them with other tools to deduce algebraic equalities or relations in various ways. A similar point is that I think students on paper often alternate between forward and backward reasoning in a way that often ends up just getting them lost or leading into mistakes of logic. For that reason, I'm really a proponent of forward reasoning wherever possible, and I limit the student's exposure to tactics that would even permit a backward reasoning style. And just for the experts, so basically the constraints I'm working around are that certain rather strong lean tactics like linearith and polyrith that contain whole algorithms that students are not really taught or capable of carrying out on paper, I somehow throw these out the window. I never teach them to my students. And I instead have a collection of weaker tactics that can replace them, but more closely match what students are able to do on paper. And I also have, as I said, a choice of tactics that limits the student's exposure to backward reasoning. The other somehow feature of the approach that I've designed is that I think it's very important to design the first weeks of a course like this carefully. At the beginning of a course like this, you really need to make sure that the students are learning some mathematics right from the start. Otherwise, the ones who are purely mathematicians with less of an interest in computer science will be frustrated. You need to capture their attention, in something that really seems like mathematics already from the start. So that they feel like they're learning something useful and to their taste, and so that they don't write off this lean business as being something irrelevant to actual mathematics. And so an important component of designing a course which is bilingual between lean and prose is that you need to come up with a tiny subset of lean that nonetheless is good enough to contain some of the mathematics you're teaching. And so designing these little sandboxes is, I think, a useful thing to do, finding a small component of your language that still lets you do some mathematics. So I have somehow two sandboxes in this way which cover the first month or so of the course. Firstly, for the first couple of weeks of the course, I only do these calculational proofs, really deducing a particular equality or inequality from a particular set of hypotheses, which are also equalities or inequalities. And as I said, this already somehow absorbs the students mathematically to a sufficient degree, because even though the students have been doing algebra for 8 or 9 years at this point, they haven't usually done algebra in this precise way of developing a single chain as opposed to a collection of chains or a collection of equations. So teaching students to reconfigure their algebraic reasoning in this way is usually good enough to keep their brains busy for the first couple of weeks of the course. And And the good news is that you can teach this with only a very small amount of lean, so only the 5 tactics that I've identified here. Then I move on to a second kind of sandbox, which lasts for perhaps another 2 or 3 weeks after that. And in that, you don't even have a full exposure to the language of logic. You see only the conjunction, disjunction, and existential logical symbols, so no implication by implication, negation, or the universal quantifier. And you restrict yourself to problems which can be phrased with only these logical symbols, which remarkably is not nothing. So in this part of the course, you can do some elementary number theory problems, and it's enough to get students used to the basic mechanics of lean, including intermediate goals and what is a definition, unfolding and refolding definitions, and developing the habit of using the info view as a reference, the goal state, while not exposing them to too much logic or too many radical transformations of goals. So by racing to this small component of elementary number theory and exactly what's needed for it, you allow yourself to cover a certain amount of lean relatively quickly, and then to take a bit of a breather where you concentrate just on this kind of mathematics and consolidate those skills, and again reassure the students that the skills that they're using are relevant to actual mathematical reasoning. So I think that's all for somehow the 2 points that I wanted to call attention to as being rather specific to the materials I've developed. But let me just, I haven't seen all the talks today, so perhaps this is unnecessary, but let me just say a little bit about general logistical things that are useful for people considering courses of this kind. And relevant to logistics also, there's a website, a page on the Lean community website, which also contains information of this kind put together by Patrick and Rob Lewis, which is a good starting point for people who are interested in the practical aspects of teaching with Lean. So the first is that I at least have found that it's important to provide a lot of access to your students. So I tend to have a lot of office hours, to rely a lot on the students' ability to invest time outside the class and think about things slowly, but to be very, very responsive to them as they are doing this thinking and coming to you with questions. And so the style of course that I've been teaching, the people who have used it have all been in relatively small classes of up to about 20 students. And I think, scaling beyond this is really not an easy problem. There have been attempts. So Rob Lewis and even at Exeter as too, I know there have been very, very big classes taught with Lean. And, my hat goes off to those people. It's a lot harder than teaching small classes. I'd like to mention the usefulness of having an online coding environment, which is something you can do with Gitpod or with GitHub code spaces, or other things like a game environment. Installing Lean is really not as easy as one would like, especially on the kind of old laptops, rather slow, that many students have. And by running Lean entirely in an online coding environment, you can totally sidestep the issues that come with installation. I've been using Gitpod very happily for 1.5 years now. I'm very happy with it. It's easy to set up and the students have 50 hours per month free. And it's just as fast on my computer as running Lean locally. For many students who have old computers, it's actually faster. Likewise, it's very nice to have what's called an auto grader, so that if the students are doing homework at home, they really can get their points entered into your spreadsheet of grades in real time. For some reason, this makes a real psychological difference to students to really hand in the homework and see the points provided instantly, rather than just handing in code which they know compiles. The difference ought to be negligible, but it really isn't. The students like the instant feedback of this auto grader, and it also saves you the hassle of opening yourself 25 different Lean files and counting the number of problems solved by each one. So it saves you an administrative burden. So I use the system written by Rob Lewis for Gradescope. There's another system available for GitHub Classroom. I think Rob will be creating other platforms worth of the same auto grader soon. And this is really a tedious setup, but a worthwhile investment in infrastructure for the course. So that's all for the practicalities, maybe just a couple of observations, anecdotal, but what I have noticed about teaching in this way. So the grading is wonderful. I teach at a school where I have to do the grading myself, and it really makes a huge difference to the grading experience to read student work, which is a somehow translation of a formal proof which is already known to be correct. There are still stylistic things that you have to teach students. They'll use words in the wrong ways, in ways that you can correct by hand. But when the bones of the proofs handed in by the students are mostly already correct, it really reduces many, many headaches. Students tend to pick up the way that, you talk about things with Lean, and this tends to help a lot with your informal discussions with students. When students already have this concept of hypotheses and goals and witnesses available, you can somehow use this as a meta language for the discussion of mathematics in a way that is surprisingly useful in informal discussions with students. I also find that for certain styles of problems, particularly the ones in which there are radical changes to how the goal is set up, like an induction where you say the magic word induction and all of a sudden your original goal has been transformed into two quite different and easier goals. These radical changes tend to be much easier for the students when they have Lean to help them. Some students, used to take a very long time to learn how to set up the two tasks in an induction, for example. And now they have immediate access to the two tasks without really having to think it through. And I think this helps them internalize it. It's that old saying, in mathematics, you don't really learn things, you don't really understand things, you just get used to them. Somehow the getting used to things happens a lot faster when some of the structure is provided by this external agent. And the same is true for certain, I guess, fiddly skills, like particularly things like inequality calculations, modular arithmetic. I really find that the bulk of the class gets this now, and before I used Lean, the bulk of the class did not get it. Things where it's easy to go wrong and where there's a precise algorithm that needs to be taught. And you can have, with the help of Lean, this immediate feedback to allow the students to iterate very quickly. This is the kind of thing where I noticed the most obvious improvement. And it's been really nice for me to be able to set problems which rely on manipulation in this way, and which I think I would not have been able to set before I taught in this way. So that's all. Thank you for listening to me talk about the way that I teach. I hope that some of it will be relevant to you in the way that you teach.
Thank you very much, Helen. Great. So we have opportunity again for any questions, comments, discussion points. I know, Patrick, I think you wanted to come in.
Yeah, I wanted to give a couple of comments about Kevin's talk first. So one I wrote in the chat already that he mentioned the sphere version project that I launched a couple of years ago, but I wanted to emphasize that although this was indeed my idea, I got a crucial reinforcement by Floris von Dorn and Oliver Nash, and I would not have been able to complete this project without them. So it was important to mention them. And talking about attribution, it's also important to remember that there are other proof assistants, and particularly people using Isabelle did formalize research level mathematics, especially in combinatorics too. And of course, the people using Coq, they maybe it does not qualify as modern research when they formalize the Fate-Thompson theorem, but it still feels weird not to mention the odd order theorem in this discussion. And so this is what I wanted to say about Kevin's talk, which was also great.
All those criticisms are definitely valid. Thank you, Patrick.
Thank you, Patrick. Thank you, Kevin. Jeremy, you put your hand up.
Sorry. I also wanted
sorry, go on, Patrick. Yeah, you wanted another one.
Very quickly about Heather's talk. So her work is of course also very important this teaching using a professor community, and there are other things that I got from her and that are mentioned in the paper, and I think I didn't mention in my talk. So for instance, this idea of getting rid of lemmas and replacing them by stacking doing the work comes from her work.
Thank you, Patrick. Jeremy?
Yeah, Heather, can you hear me?
Yes, you can.
Okay, great. So Heather, thank you for a wonderful talk. I just have a question about mechanics. So I'll be teaching interactive theorem proving again in the fall. And I hadn't considered this idea of having people come in and do lean, in front of you. So I don't know, maybe you could say a little bit more about that. Do you give everybody the same task, or do you have a small collection of them that you rotate through?
Yeah, so I usually I have I tend to be able to get through, so I give two problems for a 20-minute interview, and then I have 20-minute interviews, which takes up, maybe 2 full days twice a semester. So it's quite an investment of time. And I have a variety of reasonably similar problems. So usually I'll sort of select 2 domains being tested by the interview, and then for each of those domains, I'll have maybe a collection of 15 problems or something, all taken from that domain in order to keep it broadly similar among the students. And I have to say, most of the students do it fine. They don't struggle too much. So really, this is designed to just sort of put the fear of God into the students. Like, you can immediately see the ones who have been copying their students, their friends' homework, and those ones really, really, really struggle. And everyone else, all of the other students, it's completely fine. That's sort of the level I aim for. And so I think aiming for just that level is useful. It doesn't need to be that hard. It just needs to be a check.
Good. Thank you.
Thank you. I'll come to the room.
A direct follow-up question.
Yeah, direct follow-up. Go on.
Direct follow-up question to Heather. Have you thought about just making that interview pass-fail and just select the sample of students randomly to reduce your workload? Because that was essentially what I was thinking about in a module with 200 students, where I cannot do 10 minutes with twice a semester with 200 students.
I mean, yes, I really don't know how you do it. I mean, one thing that I would also suggest is that if you've got an existing coding project course at your university, which many universities do, speak to the people in that course and see how they handle the plagiarism question, because it's very similar, I think. So I guess you're right. I hadn't considered the random selection idea, but it's quite an interesting one. I'm not sure whether I think that's fair.
It's not fair by definition.
Yeah.
It is random.
To be more concrete, my idea was let them explain something that they already did and marked. And if they pass, they get the mark for the submitted version. And if they cannot explain it, then they get penalized. That was the idea.
That's a very interesting idea. I think it could well work. I think the question of how to, the enforcement question, it's not a fun one, but I think it really is something that needs to be explored. One other thing I'll say is that, when I look at what students submit, I'm pretty sure I can tell who plagiarizes and who doesn't. Like, they're usually not very creative in their plagiarism. But I'm hesitant to, assert that so-and-so has plagiarized or not, simply based on my own guesses. Even though I'm fairly confident in these guesses, I don't think I could defend it sort of in a university court, so to speak. And so I'm hesitant to assign credit, or for having or having not plagiarized based on my own guesses. So depending on how you fall on that question, you might simply choose to, cast an eye yourself over what's being submitted, and to directly assess yourself whether you think plagiarism is occurring or not.
Thank you, Heather. Jim. Yeah, I'll come to the questions in the chat in a moment. Jim, do you want to just come in with your question?
Thanks a lot, Heather. Very, very nice talk. So for waterproof, what we do is we try to eliminate all rewrites. So waterproof is similar to lean verbose, but we try to eliminate rewrites because we feel there's no good equivalent there. I saw very briefly on your slide that you have an opinion about rewrites, but I saw it only too short to really understand your opinion. So can you elaborate on that? What is your opinion on using rewrites?
So I very much agree, but what I would do is distinguish, and I'm not sure if you also make this distinction between rewriting and congruence. So I permit congruence, that is, and in fact, I make heavy use of congruence, which is, if you have, a certain elaborate function of A and a certain elaborate function of B, if you know that A equals B, then the corresponding relationship also holds between the elaborate functions of A and B. And under circumstances which I also use heavily, generalized congruence. If A is less than B, and you have the right kind of complicated function taken, then complicated function of A is less than complicated function of B. So this is, in a way that's reasonably precise, as in we have, lean tactics for rewriting that are based on underlying congruence tactics. Like, so this is a component of rewriting, but it's not all of rewriting. And I feel like, in fact, in mathematical practice on paper, a lot of the things that are called rewrites and taught as rewrites are actually just congruence. And so at some point I would like to actually ban rewrite from the course and just use congruence. At the moment, for slightly technical reasons, I'm not doing that, but that's where I'd like to get to in the end.
Okay, thanks a lot.
Yeah, thank you very much. And thanks to Evgenia, who's put the question in the chat for Kevin. How do people tend to search for the needed theorem while formalising maths? Google.
Moogle.
Moogle. Okay.
Or they love it. They love it. It once went down for about 6 hours and there was panic, widespread panic in the computer room.
Okay.
They all use Moogle. And yeah.
Okay, thank you. And Alvaro, again for Kevin, do you believe Lean can surpass traditional proofwriting in the future in terms of research and published works? Or will we ditch paper-written proofs?
No.
Okay. A simple answer. Okay, last opportunity for any further comments, questions before we break. Okay, let's just thank again Kevin and Heather. Okay. Thank you.